Hello, physicists. Welcome to another edition of Dr. Physicist's Greatest of All Time.
It is so great to be here. I'm really excited for this one.
Oh, same here. Because today we are doing a deep exploration into the life and work of a man that, well, Albert Einstein himself called the greatest mind in American history.
Which is just a massive statement. I mean, coming from Einstein.
Right. And yet, if you went out on the street right now and asked someone who Josiah Willard Gibbs is,
They'd probably just stare at you.
exactly, complete silence, which, as we're going to see from our sources today, is incredibly fitting.
Yeah.
Because silence was kind of his whole brand.
It really was the ultimate paradox. I mean, we always expect these huge paradigm shifts to come with a lot of noise.
Oh, totally. We picture, like, a charismatic genius at a chalkboard.
Yeah, in some packed European lecture hall, debating rivals, soaking in the applause.
Getting into newspaper feuds.
Right, exactly. But the guy who mathematically rewired our entire understanding of the universe, he never raised his voice.
He didn't want any headlines.
Nope. He lived this incredibly quiet, uneventful bachelor's life, mostly staying within, like, a 3-block radius in New Haven, Connecticut.
It's wild. So our mission today, and for you listening at home, is to really decode this guy. How does a man who avoids the public eye like a plague, who publishes in completely obscure local journals, and who apparently mumbled through his own lectures?
Yeah, he was notoriously unintelligible to his own students.
Right. How does that guy single-handedly lay the foundations for modern physical chemistry?
And statistical mechanics,
And vector calculus.
which literally dictates how your car battery works,
Right.
right? And, how the universe will eventually end.
The stakes are just a little high.
Just a bit. So we've got a fantastic stack of sources for this. We're pulling from biographical articles from the Mystic Stamp Discovery Center
We also have some really dense historical analyses from the American Journal of Science.
and a bunch of deep excerpts detailing the history of Maxwell's equations and classical thermodynamics. So we're really getting into the weeds here.
It's going to be fun. It is. And as we go through this, I want you, the listener, to keep this central mystery in mind. How did a guy who started out obsessed with the literal, physical, world-like designing train brakes,
Yeah, literal gears and brakes.
how does he realize that to master physics, he has to completely abandon the physical world for pure math?
It took a massive pivot.
Right. So let's set the stage. Let's look at his pedigree, because it is, frankly, staggering.
Oh, it really is. So he's born on February 11th, 1839 in New Haven.
And he doesn't just come from an academic family. This is like American academic royalty.
Oh, absolutely. I mean, his paternal ancestor, Samuel Willard, was actually the acting president of Harvard.
From what, 1701 to 1707?
Yeah, way back. And then on his mother's side, you have Jonathan Dickinson,
The first president of the College of New Jersey.
which is Princeton. So, the academic roots run incredibly deep.
It's just steeped in scholarship. But even just looking at his dad, Josiah Willard Gibbs Sr., he was a professor at Yale Divinity School.
Right? A professor of sacred literature. And he's actually remembered for a really public, incredibly important historical event.
The Amistad Mutiny, right, in 1839.
Exactly. So when the African captives of the Amistad took over the slave ship and ended up imprisoned in New Haven, it was Gibbs Sr. who stepped up.
He realized they needed a voice in the legal system.
Right. They couldn't defend themselves because of the language barrier, so he actually wanders around the docks of New York just counting out loud in the Mende language.
Wait, he just walked around counting out loud?
Yeah, hoping someone would recognize the dialect, and he actually found a sailor who did, which meant they finally had an interpreter.
Wow. And that allowed them to testify and eventually get their freedom.
Exactly. So you have a father who is out there in the public eye, actively using language to secure human freedom in a very real, high-stakes way.
And then young Willard grows up at that exact same house, right, like a block from Yale.
Yep.
But he ends up retreating into an office to silently calculate the freedom of chemicals.
It is a really stark contrast.
Yeah, I mean, was it a rejection of his dad's public life? Like, I don't want any of this noise.
Well, the sources actually suggest it wasn't a rejection at all. It was more of a translation.
And translation, how so?
Because from his father, he learned that language isn't just for casual chatting, it's a structural tool for uncovering truth.
Oh, interesting.
Right. His dad used linguistics to decode justice. Gittins just swapped the medium. He used mathematics as a language to decode physical reality.
Okay, I love that. The medium changed from the courtroom to the cosmos. but it's still about using a precise language to find order.
Exactly. And you really see this in his early education. He goes to Hopkins Grammar School, and he's described as, friendly but super withdrawn.
Yeah, the sources say he had delicate health and mostly kept to himself.
But his brain was clearly on another level. He gets to Yale at age 15.
Age 15.
Right. And he just sweeps up all these prizes in Latin and mathematics.
Which again plays right into that language thing. Latin is so structured, so rule-based.
Exactly. For him, math wasn't just about calculating the stress on a bridge. It was the fundamental grammar of the universe.
So he graduates near the top of his class in 1858, hangs around Yale, and then in 1863, he makes history.
He really does. He earns the very first Doctor of Philosophy, the first PhD in engineering ever granted in the United States.
The very first one.
Yeah.
But here's the wild part to me. We know him as this master of invisible, abstract physics, right?
Yeah, the guy mapping the cosmos.
But his thesis topic is so grounded. It's literally titled, On the Form of the Teeth of Wheels in Spur Gearing.
He wrote his historic PhD on gear teeth.
Like physical metal gear teeth.
Why?
Why was a mathematical genius looking at gears?
Well, you have to look at the American intellectual landscape at the time, mid-19th century. It was all about empirical, pragmatic invention.
Right, it's the era of the Transcontinental Railroad. The telegraph.
Science in America meant things you could touch, build, and sell. It wasn't about abstract theory.
Yeah. New Haven alone had Charles Goodyear doing vulcanized rubber and Eli Whitney with the cotton gin. It was a city of tinkerers.
And Gibbs was fully immersed in that. But even with the gear teeth, you see his unique approach.
How so? Like, what was the actual problem with gears back then?
So if industrial gear teeth weren't shaped absolutely perfectly, the angular velocity would fluctuate just a tiny bit as they meshed together.
Which causes friction.
Massive friction, vibration, wear and tear on heavy machinery. And the standard American way to fix this would be to just go into a workshop and file down the metal until it kind of worked better.
Just trial and error. Brute force.
Right. But Gibbs didn't do that. He applied pure, rigorous geometric analysis. He studied involute curves.
Remind me, an involute curve is...
It's the mathematical curve you get if you trace a point on a taut string as you unwind it from a circle.
Okay, got it.
And he proved, mathematically, that if you shape the gear teeth using an involute profile, you guarantee a constant transmission of rotational force.
So it doesn't even matter if the center distance between the gears shifts a little bit.
Exactly. The geometry solves the physical problem perfectly.
It's like he started his career optimizing the physical gears of a machine, only to realize the real truth is in the geometry itself.
Right. The iron and steel are secondary. The math is what's real.
So he gets his doctorate, and he tutors at Yale for 3 years teaching Latin and natural philosophy.
And he even patents a mechanical railway car brake in 1866.
Which is amazing. A brake that uses the train's momentum to synchronize the braking across all the cars.
It's very clever, practical design.
But, physical gears have friction, they break. And I feel like Gibbs realized that if he really wanted to optimize nature, he couldn't do it with iron.
No, he needed a language with zero friction. And that realization is the turning point of his entire life.
Because he clearly exhausted the limits of what American pragmatism could offer him.
He absolutely did. To find that frictionless language, he needed a huge catalyst. He needed to leave the American mindset entirely.
Which leads us to the Grand Tour.
Right. So between 1866 and 1869, unfortunately, both of his parents pass away.
Yeah, which is tragic. But it leaves him and his 2 sisters, Anna and Julia, with a modest inheritance.
And they use it to travel to Europe. But this wasn't a vacation to mourn. This was an intellectual awakening.
They hit all the heavy hitter spots.
Yeah.
Paris, Berlin, Heidelberg.
In Paris, he's attending lectures by Joseph Leerville, this brilliant mathematician. In Berlin, he's studying under Karl Weierstrass and Leopold Kronecker.
The absolute titans of math.
And the chemist Heinrich Gustav Magnus. But Heidelberg is where his brain gets completely rewired.
Because he runs into Gustav Kirchhoff and Hermann von Helmholtz.
Exactly.
So for our listeners, what were Kirchhoff and Helmholtz doing that the guys in New Haven weren't?
They were unifying things. While Americans were just trying to build a faster steam engine, the Germans and French were asking fundamental questions.
Like, how does heat relate to light? How does electricity fit in?
Yes. They were moving away from just observing physical machines and moving into rigorous mathematical physics and field theory.
They were writing the equations for invisible phenomena.
And Gibbs just soaked all of this up. He realized that the ultimate truth wasn't in the machine itself, but in the mathematical symmetries governing it.
It's a total paradigm shift for him.
But the trip almost ended in disaster. He actually had a severe tuberculosis scare.
Oh, right. They had to flee to the French Riviera.
Yeah, the warm climate was basically the only treatment back then. Thankfully, he healed up, and they sailed back to New Haven in 1869.
But the guy who gets off that boat is not the same guy who left. His intellectual horizon is just blown wide open.
Entirely transformed. So in 1871, Yale appoints him as the professor of mathematical physics.
Which, by the way, was the very first professorship of its kind in the U.S.
It was. But there's a pretty massive catch to this job offer.
Yeah, Yale appointed him without a salary.
$0. For the first 9 years of his professorship, Josiah Willard Gibbs did not draw a single penny.
I mean, let's just pause and think about that. You have this guy sitting in a Yale office for almost a decade. No salary.
And he didn't publish a single paper during that time either.
Today, a university would fire you so fast. The dean would be screaming, "Where are the grant proposals? You're taking up an office."
Oh, totally. You'd be out the door in a year.
What does that say about Yale back then? Or just his own character, that he just sat there in silence?
Well, Yale tolerated it, probably because he wasn't costing them anything.
Fair point.
But for Gibbs, it shows this almost monastic devotion to his thoughts. He had absorbed this advanced European framework, and honestly, there was no one in America who could even understand the math he was doing.
So he was intellectually isolated.
Completely. He just lived off his inheritance, sat in his office, and spent 9 years building an entirely new architecture of thought.
Just incubating. And when he finally breaks that silence in 1873, it's explosive.
Oh, it sent shockwaves. But the craziest part is how he communicated it. He didn't just use standard algebra, he used pure geometry.
Right. He publishes 2 major papers in 1873, Graphical Methods in the Thermodynamics of Fluids and A Method of Geometrical Representation. Oh, it's a very long title.
Of the thermodynamic properties of substances by means of surfaces.
Catchy.
Very snappy. But essentially, he took thermodynamics and turned it into a visual 3D topographical map.
Which is mind-blowing. Before this, thermodynamics is mostly just, steam engine science.
Right. Carnot, Joule, Clausius, they did brilliant work on heat transfer and entropy.
But it was all fragmented, right? Like an equation for pressure here,
Yeah.
an equation for volume there.
Exactly. It was disjointed. Gibbs turned it into a universal science. He proved mathematically that you could capture everything about a fluid's thermodynamics with just 3 variables.
Volume, energy, and entropy.
Yes.
So imagine you're staring at this massive, incomprehensible spreadsheet of data. Just columns tracking how a gas acts when you heat it or squeeze it.
Just a wall of numbers.
And Gibbs takes that spreadsheet and he plots volume, energy, and entropy as x, y, and z coordinates.
And suddenly, that spreadsheet becomes a physical, 3-dimensional landscape, a thermodynamic surface.
You can literally see the hills and valleys of energy.
And the geometry wasn't just for show. The specific slopes and curves of this shape corresponded directly to physical properties.
Like, if you calculate the tangent plane rolling over the surface, the angle of that plane gives you the exact temperature and pressure.
It's beautiful. You could just look at the geometric shape and know exactly when water would boil or freeze.
And this purely theoretical visualization actually catches the attention of someone huge across the Atlantic.
James Clerk Maxwell.
The guy who unified electricity and magnetism.
The absolute titan of physics. Maxwell reads Gibbs's papers over in Cambridge, England, and he immediately sees the genius.
He recognized that Gibbs had essentially mapped the invisible laws of energy.
He was so blown away that he spent an entire winter in his lab working with clay and plaster.
Wait, Maxwell himself did this?
With his own hands. He sculpted a physical 3D model of Gibbs's thermodynamic surface for this fictitious, water-like substance.
I just picture Maxwell, this towering figure in science, covered in plaster dust, carefully carving out entropy curves.
And then he boxed up a copy of this plaster cast and shipped it across the ocean to Gibbs at Yale.
That is the ultimate scientific compliment. But I have to ask, why did it take Maxwell, sitting all the way in England, to validate him?
Why didn't someone at Harvard do it?
Yeah, why not an American?
Because the American scientific community didn't have the theoretical vocabulary. They were still obsessed with making better train boilers.
They couldn't read the math.
Right. Gibbs was operating at a level of abstraction that didn't exist here yet. Maxwell spoke his language fluently.
That makes sense.
Yeah.
But as brilliant as those 1873 graphical papers were, the sources say they were just a warm-up.
Oh, he was just stretching his legs. The geometric surfaces were just a tool.
He was gearing up for his masterpiece,
Mm.
stepping away from simple fluids like water and looking at the absolute chaos of chemical reactions.
Right. So between 1876 and 1878, he drops this massive 300-page monograph.
On the equilibrium of heterogeneous substances.
And this is the paper that historians like Bill Bryson refer to as the Principia of Thermodynamics.
Just like Newton's Principia defined gravity and planetary motion, Gibbs defined how matter and energy interact on a chemical level.
He gave chemistry its mathematical soul.
Let's break down the sheer scale of this, because he introduces concepts here that literally run modern industry, starting with chemical potential.
Chemical potential is the driving force of all chemical reactions.
Okay, give me an example.
Think of a sealed container that has solid ice, liquid water, and water vapor all in it at the same time.
A multi-phase system.
Right. Before Gibbs, scientists couldn't mathematically predict how much ice would melt or vapor would condense under different conditions. It was a guessing game.
But Gibbs solved it.
He proved that for this system to be in perfect equilibrium, meaning nothing is actively changing state, the chemical potential of the water molecules must be exactly the same in the ice, the liquid, and the vapor.
So if the potential is higher in the ice melts until everything equalizes.
Exactly. It's the thermodynamic equivalent of gravity causing water to seek its own level.
He found the gravity of chemistry. That's incredible. And then he introduces something that, if you've ever taken a chemistry class, gives you flashbacks. Gibbs Free Energy.
Oh, yes. The famous equation, G equals U plus PV minus TS.
It looks so simple on the surface, but let's unpack the mechanics of that equation for everyone.
Okay, so G is the Gibbs free energy. U is the internal energy of the system. P and V are pressure and volume, and T and S are temperature and entropy.
Got it.
What this equation is actually describing is a battle. The universe has two competing desires. First, physical systems want to minimize their energy.
Right, like a ball naturally wanting to roll to the bottom of a hill.
Yes, that's represented by the enthalpy, the U plus PV part. But the second desire is that systems want to maximize their entropy, their disorder.
Like a drop of ink spreading out in a glass of water. It wants to be messy.
Exactly, that's the S part. So nature is this constant tug of war between laziness wanting low energy and messiness wanting high disorder.
And temperature, the T, is the multiplier for the messiness.
Right. At high temperatures, the drive for disorder dominates. At low temperatures, the drive for low energy wins out.
And Gibbs took these competing drives and combined them into one variable, the free energy, G.
And he proved that for any system kept at a constant temperature and pressure, which is how almost all lab experiments are done, any spontaneous reaction has to lead to a decrease in G.
So equilibrium is only reached when G hits its absolute minimum.
Yes.
So, practically speaking, if I'm an industrial chemist and I want to know if mixing two chemicals is going to cause an explosion or just sit there,
You don't have to guess. You don't have to risk blowing up your lab.
I just calculate the Gibbs free energy on paper. If G goes down, the reaction happens spontaneously.
He literally gave humanity a mathematical crystal ball for matter. He built the deductive foundation for all physical chemistry.
And he didn't stop there. In the same paper, he derives the Gibbs phase rule, F equals C minus P plus 2.
Right, which relates the degrees of freedom, F, to the chemical components, C, and the physical phases, P.
Let's ground this for the listener. Why does that specific equation matter outside of a textbook?
Well, let's look at the Haber process. Early 20th century, humanity is facing a huge crisis. Natural fertilizer reserves are running out.
Right. And without fertilizer, global agriculture collapses. Billions starve.
The atmosphere is 78% nitrogen, which is perfect for fertilizer, but it's incredibly stable. It refuses to react with hydrogen to make ammonia.
So chemists were just randomly heating up vats of gas, hoping for a reaction, and getting nothing.
Exactly. Until Fritz Haber and Carl Bosch used the principles Gibbs laid down. By understanding the phase rule and chemical equilibrium, they didn't have to guess.
They calculated it.
They calculated exactly how manipulating the degrees of freedom, like drastically increasing the pressure while tuning the temperature, would force the equilibrium point to shift.
And they artificially forced the nitrogen and hydrogen to combine into liquid ammonia.
Gibbs's abstract math allowed them to pull fertilizer literally out of thin air. Without the equations he wrote in that silent room, the modern population of the Earth could not be fed.
He saved billions of lives with an equation. He basically wrote the operating manual for industrial chemistry and metallurgy.
He really did.
But this is the part of the story that drives me absolutely crazy. He writes this masterpiece, The Principia of Thermodynamics.
The puzzle is solved.
Where does he publish it? Does he send it to the Royal Society in London? Or some top-tier German physics journal?
Nope. He publishes this 300-page revolution in the Transactions of the Connecticut Academy of Arts and Sciences.
A journal so obscure it was basically a local newsletter for New Haven intellectuals.
It's absurd.
Why? Was it arrogance, like I'm so smart, people will find it no matter where I hide it? Or did he just not care?
From everything we know, it was a profound lack of ego, mixed with this hyper-localized sense of duty. He was a member of the Connecticut Academy, so he felt obligated to support local publishing.
But the irony is devastating.
Yeah.
The editors openly admitted they couldn't even follow the math in his paper.
They published it entirely on faith. And worse, they didn't even have the budget to print a 300-page paper full of complex equations.
Oh, right, they had to pass the hat around.
Yeah, they had to raise funds through private subscriptions from local businessmen. Guys who definitely didn't understand Gibbs Free Energy were paying the printer.
It's like finding the cure for all diseases, and instead of calling the World Health Organization, you post it on a neighborhood watch blog with 50 readers, and you make your neighbors pay for the web hosting.
That is exactly what happened, and the consequence was that the global scientific community remained largely ignorant of his work for over a decade.
Brilliant physicists in Europe were accidentally reinventing fragments of his work, having no idea the perfect solution was sitting in a dusty journal in Connecticut.
It wasn't until Wilhelm Ostwald translated it into German in 1892 and Le Chatelier translated it into French in 1899 that the world realized an American had beaten them all 20 years prior.
Unbelievable. But Gibbs wasn't just sitting around waiting for translations. He was moving on.
He expanded his focus to general physics, electromagnetism, light.
But he ran into a major roadblock. The mathematical tools of the day were clunky. They had too much friction.
And remember, for Gibbs, math is a language. If the language isn't efficient, you can't describe reality properly.
So what do you do when the language fails? You invent a new one.
Which brings us to the math wars of the 1890s.
The math wars. I love this. So, to understand this war, we have to look at the reigning mathematical champion at the time, quaternions.
Right. Developed by the Irish mathematician William Rowan Hamilton in 1843, quaternions were a four-dimensional algebra.
Hamilton famously carved the formula into a bridge in Dublin during a flash of inspiration.
It had this very romantic, cult-like following among mathematicians because mathematically, quaternions were elegant. They had internal algebraic completeness.
It's one real number, a scalar, and three imaginary numbers defining a 3D space.
Exactly. But if you're a physicist just trying to calculate the trajectory of a cannonball or the flow of a magnetic field,
having to carry around that extra imaginary fourth dimension in every single calculation is a nightmare.
it's a massive, cumbersome headache.
It's like trying to give someone simple driving directions to the grocery store, but the map requires you to calculate your position relative to the center of the Milky Way.
Beautiful math, but utterly useless for driving.
So Gibbs looks at this and decides it's way too complicated for practical physics.
Force has magnitude and direction. That's all he needed. So, working independently of Oliver Heaviside, who was also frustrated by this, Gibbs did something mathematically violent.
He ripped quaternions apart.
He separated the scalar part from the vector part, threw away the complexities he didn't need, and developed the foundation of modern vector analysis.
If anyone listening has taken high school or college physics, you know exactly what Gibbs created.
The dot product, the cross product.
And the del operator, that little upside-down triangle for calculating gradient, divergence, and curl.
Let's explain this mechanically. The dot product tells you exactly how much one vector, like a force arrow, is pushing in the same direction as another.
Like calculating how much work you do pushing a cart up a hill.
Right. And the cross product calculates the perpendicularity, how much those forces act at right angles.
Which you need for torque or understanding magnetic fields. So Gibbs prints a pamphlet of these new rules in 1881 and 1884.
But just as notes for his Yale students, he didn't even publish it as a book. It took his student Edwin Bidwell Wilson to expand it into a textbook in 1901.
But the math establishment in Europe did not see this as a helpful tool. They saw it as heresy.
They were furious. It sparked this huge debate in the journal Nature. The quaternion defenders were led by a Scottish physicist named Peter Guthrie Tait.
And Tate hated Gibbs's vectors.
He despised them. He called it a mutilation of Hamilton's elegant creation.
Hmm.
To Tate, Gibbs was an intellectual vandal destroying mathematical perfection just for convenience.
Right. Tate thought Hamilton handed physicists this beautiful, infinitely complex Swiss Army knife with 50 attachments.
A true work of art.
And Gibbs comes along, violently snaps off the 48 blades he doesn't need, throws them in the trash, and says, look, I just need a really good scalpel.
And Tate is screaming, "You broke the knife?"
It's a perfect analogy. But Gibbs defended his system with poor logic.
He argued that for a physicist, math is an operational language. It has to map directly onto physical reality. Quaternions required translating forces into 4D algebra and then translating it back to 3D.
While Gibbs's vectors map directly onto the 3D space we actually live in.
His scalpel allowed physicists to describe electromagnetic fields seamlessly.
Think about it. How much of modern physics would even be readable today if Tate had won and we had to use quaternions?
Almost none of it. Aerospace engineering, weather models, electrical grids, it all relies on Gibbs's dot and cross products. He won the war through unmatched, brutal, practical utility.
And armed with this new scalpel, Gibbs starts tackling the deepest mysteries. He moves from chemistry to the fundamental nature of light itself.
In the 1880s, he applies his vector analysis to Maxwell's electromagnetic theory of light. He investigates physical optics.
Like birefringence, right? Double refraction.
Exactly. When you look through a calcite crystal and see a double image. He also studied dispersion, how a prism separates white light into a rainbow.
Now, at the time, physicists were incredibly confused about how light actually traveled through space.
Right, because they knew sound needed air to travel, so they assumed light needed a physical medium too.
The luminiferous ether.
Yeah.
They were making up all these complex, jelly-like mechanical models of an invisible ether.
And Gibbs just cut through all of that guesswork. Using rigorous vector math, he showed you didn't need an imaginary ether.
He proved Maxwell's equations could account for all of it perfectly on their own. And he proved light doesn't have a longitudinal wave.
Let's clarify that. A longitudinal wave like sound travels by compressing and expanding the medium in the direction it's moving, like pushing a slinky.
Right. But Gibbs proved light waves are purely transverse. They oscillate perpendicular to the direction of travel, like plucking a guitar string.
By proving that purely through equations, he stripped physics down to mathematical relationships, helping lay the groundwork to finally abandon the mechanical ether altogether.
He's cleaning up optics. He cleaned up chemistry. But he was saving his most mind-bending work for the very end of his life.
1902. Just a year before he died, he publishes Elementary Principles in Statistical Mechanics.
He actually coined the term statistical mechanics, didn't he?
He did. And to understand how huge this is, look at the glaring gap in 19th century physics. Gibbs had mapped macroscopic thermodynamics, bulk matter, pressure, temperature.
But they knew the universe was made of microscopic atoms. The ultimate question was, how do random, chaotic collisions of trillions of microscopic particles create the perfectly predictable macroscopic laws?
Right. How does the chaos of the micro create the order of the macro? It's a massive scaling problem.
Boltzmann and Maxwell tried tackling this by calculating the velocities of colliding gas molecules.
But that required making specific assumptions about what atoms look like and how they bounced. Gibbs wanted a more general approach. He knew tracking 10 to the 23rd particles was mathematically impossible.
So he makes this huge conceptual leap. He introduces the ensemble.
The ensemble. It sounds musical, but in physics, it's a staggering thought experiment.
Walk us through it. How does it bridge the micro and the macro?
Okay, imagine you have a sealed glass box on your desk filled with gas. Instead of trying to track every molecule in that one box, Gibbs said, imagine millions of identical virtual boxes.
A whole multiverse of boxes.
Exactly. Every virtual box has the exact same amount of gas, but the microscopic arrangement of the molecules is slightly different in each one. Every possible microstate is represented.
So you're creating a probability density in what physicists call phase space.
Yes. And he defined 3 specific types of ensembles that are still the gold standard today. First, the microcanonical ensemble.
Okay, what's that one?
It's an ensemble where energy, volume, and particle number are absolutely fixed, completely isolated universes.
And the second?
The canonical ensemble. Here, the volume and particle number are fixed, but the boxes are submerged in a massive heat bath. So the overall temperature is fixed, but the internal energy of any specific box can fluctuate.
And the third one?
The grand canonical ensemble. This is the most complex. The walls of the virtual boxes are permeable. They can exchange both energy and particles with their surroundings.
Wow. And that links right back to his early work on chemical potential, right? Because chemical potential dictates that exchange of matter.
Exactly. It all tied together.
Let me make sure I'm grasping the gravity of this. He proved mathematically that you don't need to track every single drop of water to understand the ocean's flow.
Right. You don't need to know what atom A is doing to atom B.
You just calculate the statistical probabilities of the entire ensemble of possible states. And by averaging that multiverse of virtual boxes, you predict the exact behavior of the one real box on your desk.
Yes. He showed that things like temperature, pressure, and even the arrow of time entropy aren't fundamental laws. They are emergent properties arising from microscopic statistical probabilities.
The audacity of that math is staggering. He builds this in 1902, but physics was about to undergo a massive earthquake. Einstein, Bohr, Planck, they discover quantum mechanics just a few years later.
Right. The classical rules completely break down at the atomic level.
So does Gibbs's statistical mechanics collapse when the quantum revolution hits?
This is the greatest testament to his genius. Because he built his ensembles on abstract phase space and general probabilities, rather than classical billiard ball models of atoms, his framework was virtually indestructible.
It survived quantum mechanics.
It completely absorbed it. Physicists realized they didn't have to throw Gibbs out. You just swap classical phase space for quantum states, and the grand canonical ensemble works perfectly.
He future-proofed theoretical physics for the 20th century before it even began.
He absolutely did.
It's awe-inspiring. He lays the groundwork for quantum mechanics, physical chemistry, everything. And yet, the man himself remains stubbornly rooted in the 19th century.
The contrast is almost comical. His mind is roaming infinite dimensional phase spaces, visualizing multiverses, but his physical body rarely left New Haven.
He lived his entire life in his childhood home, never married, shared the house with his sisters.
Yeah, Julia married the Yale librarian Addison Van Name, and Gibbs just stayed on as a bachelor lodger.
But the sources are careful to point out, he wasn't some bitter hermit. He was a dignified gentleman. He took his carriage out for drives. He was a good horseman.
And meticulous about household chores. The man who wrote the universal laws of chemical equilibrium was a designated salad mixer in the house.
Which makes perfect sense, mixing fluid phases until they reach thermodynamic equilibrium.
Exactly. He took great pride in his salad dressing, and he was known to be kind to his students, even if his lectures were dense.
He didn't seek power at Yale, wasn't a firebrand, but there was that one famous outburst at a faculty meeting.
Yes. The faculty was deeply divided, arguing over whether to emphasize classical languages or the new elective sciences.
And Gibbs, a guy who mastered Latin and math, who spent years unpaid, finally stands up.
He addresses the warring faculty and delivers a profound 5-word defense. Mathematics is a language.
Drops the mic and sits down. The ultimate synthesis of his worldview. And while he didn't seek the spotlight, his legacy lived on through his students, like Edwin Bidwell Wilson with vector calculus.
And Irving Fisher, who became a massively influential economist. He took Gibbs's rigorous modeling of equilibrium and applied it to economic markets.
And Lee DeForest.
Right. DeForest took Gibbs's physics courses and went on to invent the Audion vacuum tube.
The first device to amplify electrical signals. It ushered in radio broadcasting, long-distance telephony, early computing.
The abstract theories of Gibbs directly birthed the electronics age.
The scientific world did eventually wake up to him while he was alive, thankfully. He won the Rumford Prize in 1880.
And in 1901, the Copley Medal from the Royal Society in London, the highest international honor before the Nobel Prizes.
He died on April 28, 1903, at 64, from an intestinal obstruction, just 2 years before Einstein's miracle year.
If he had lived just a little longer, he undeniably would have been among the very first Nobel laureates.
The posthumous honors flooded in: the Willard Gibbs Award, the Hall of Fame for Great Americans, a U.S. postal stamp in 2005.
There's a Gibbs crater on the moon, and the U.S. Navy named an oceanographic research ship after him.
Even artists saw the beauty in his math. The poet Muriel Rukeyser wrote his biography in 1943. She saw how his math revealed a magical world where water could freeze on a fire or salt could spontaneously pile up.
He did for thermodynamics what Laplace and Newton did for celestial mechanics.
But I keep coming back to his silence. It is so rare to see a genius utterly devoid of ego. He knew his significance. He mailed his 300-page paper to Maxwell, but he did nothing to promote himself.
He was completely serene. He knew posterity would figure the math out.
In our era of relentless self-promotion, his confident silence is just deafening.
He didn't need a PR campaign. He knew the equations were true and the universal language of math would endure.
We have been on quite a journey today. From an American engineer optimizing gear friction to a guy drawing geometric maps of invisible energy while working for free.
Writing the Principia physical chemistry, inventing vector calculus with a scalpel, and creating statistical mechanics for the quantum age.
His life's work unified chaotic, disparate facts into a singular, elegant structure. And that brings me to a final thought for you, the listener.
Ooh, I like where this is going.
Gibbs lived in a time of rapidly expanding experimental data. Scientists were discovering isolated facts about heat and electricity that baffled them.
They were just drowning in disconnected data, running more experiments, hoping the sheer volume would reveal the truth.
But Gibbs didn't run another experiment. His solution to a chaotic world of data was to step back, sit in a quiet room, strip away the physical noise, and find the underlying harmony.
In our modern age, we suffer from severe information overload. We are drowning in a tsunami of daily data and noise, but we're starving for actual wisdom.
Exactly. Perhaps the ultimate lesson of Josiah Willard Gibbs is that true clarity doesn't always come from gathering more information. Sometimes it only comes from finding the right language to finally understand the information we already have.
The muddy waters of endless data only clear when you apply the right theoretical lens. He gave humanity that lens.
He certainly did. Thank you to our global audience for tuning in to Dr. Physicist's greatest of all time. Keep questioning the world. Keep looking for the hidden mathematics governing the chaos around you. And remember that sometimes the quietest voices echo the longest. Until next time.